All right. Hi, everybody. Welcome to the World Campus Tech Club Malware Hunting with Machine Learning Malware Threat Intel presentation. Our speaker is Saket Upadhyay. Did I say that correctly?
Yeah.
He is a cybersecurity researcher and student at, I honestly did not understand how to pronounce the school you're going to.
VIT, you can say.
VIT.
Bhopal.
In where?
Bhopal, India.
Bhopal, India, yeah. So everybody, give them a warm welcome, and you take it away, Saket.
All right, so hi everyone. Let me just share my screen fast. Let's see. Next. Yeah. Can you see my screen?
Yes.
Yes.
All right. So hi everyone. I'm Saket, and we will just get started with the presentation, and I will tell you about myself. So I am an independent security researcher, and I'm interested in malware analysis, reverse engineering, and I just came into machine learning field, and I'm just now working on combining these two so that we can develop new technologies. And I have worked in some companies as pen tester and vulnerability analyst, and I have 5 years of experience in the field, including the research I'm doing and the learning bits. And currently I'm pursuing bachelor's from VIT Bhopal in cybersecurity and digital forensics. So let's get started with the topic. So we will start with the basic malware definitions so that we have a base to start, and then we will build on it till machine learning technologies. All right? Okay, so first we will start with what is malware and how we define malware and what we understand from it. And this will create a base for our detection. So what we look for in the malware and etc. Then we will see basic detection methods that are already being used in antiviruses and other products which detect malware, and how we actually do it now and before machine learning process. Then we will get into the basic idea of machine learning in malware detection. And we will see why we need machine learning and how we can detect malware from machine learning. Then we will dive deeper into the machine learning process, and we will see how we can extract features from malware samples, what we actually look for in malware to train our models. Then we will see how training and testing of models works, like when we have featured and then how we train them. Then we will see how we can evade these detections, single model detections. So first we will get to the training part. We will create our own model and we will train it. And I have some demos for you guys so that we can see how it actually works. And then we will try to evade those single model detections. And then we will talk about how we can integrate multiple models to get rich threat intelligence and insight into malware trends. Then at last, we will try to conclude it, and we'll have a question and answer just in case anybody has a doubt. And if you have any doubt in between, you just write it in the chat section, I guess, in Zoom, and I will try to, say it till then. All right. And okay, so let's get started. So what is malware? So any software that is intentionally designed to cause damage to a computer. This is the most basic definition we came across when we search for malware in Google or any other search engine. So this is the most basic definition of malware. Any software that's intentionally designed to cause damage. So there's wide variety of malware right now. So we are talking about viruses. The first virus was the creeper system, which was uh, made accidentally in 1971. Then we have worms. The Morris worm was the first one in 1988. Then we have Trojan horses, applications which seem to be something else, but they are something else inside. They seem to be harmless, but they are harmful applications inside. So the first incident of Trojan horse was animal Trojan horse in 1975, and so on. We have ransomware, and uh, the WannaCry ransomware is a great example of how ransomware works. Then we have spywares, the software which spy on you and will not alter your you know actual workflow, but it will spy on you and it will send data to the CNC, uh, control and command center. Then we have adware and scareware. So scareware will just you know inject fear and hate in people. It will not actually destroy your data. It's just a kind of emotional malware, you can say. So it will just play with target's feelings. So these are some kinds of malware that exist today, and we will try to identify them, and we are trying to minimize their effect on regular workflow. So from the definition and what we already know, we can see that malware has these properties in them. First of all, they steal data. So, we can say they copy data, they move data. So these file operations they perform. Then they encrypt data in case of ransomware. So we are seeing file modification calls here, right? So to encrypt data, they have to call for some file modification functions. Then they delete sensitive data. So we are seeing mixture of file modification and manipulation here. There's difference between manipulation and manipulation, a slight difference between them. So yeah, and then we see they alter or hijack core computing functions and system calls, etc. So we will check for these in when we are scanning for malware. Then they monitor users. So we can check for active processes, process hooks, etc. The process which is monitoring everything in the computer or which seems suspicious by behavior. Then we have process hijack, memory injection, and so on. So one interesting thing we see here is that these computing functions are pretty normal, right? It is not just that a malware will only do that. We also copy and move files. We also modify our files. We also encrypt our files in our systems. And we also use these memory injections and active processes because we have parental controls, etc., which monitor user activity. And the memory injection, a very good example of memory injection is when we try to debug a software. We inject the debugger or uh, the software which is used inject some specific code uh, in there to call signal interrupts, etc. So to pause the process and debug it. So these are not just a sure short way to say that this is a malware. We also do it. It is the combination of these properties that we see. So we will see further into it. So let's talk about malware infection vectors. So when we talk about malware, most of people say it's just like an executable. But malware can be any script, an executable. It can be contained in a file. We have droppers. They drop malware by other methods. So if we talk about executables, let's take three major platforms: Linux, Windows, and Mac. So they have these extensions which are executable. Like Windows have exe, MSI, VBS scripting, batch scripting, PowerShell scripts. They can be executed. Then Linux has shell scripts and ELF, executable Linux file. Then Mac has app and package files. So these can be executable malwares. They can be executed. Then we talk about documents, and most of the time documents act as a payload or a dropper. So when we download a document that malicious, that will contain these executables or other formats, and it will act as a carrier for the specific malware. So let's take three major document formats again: PDF, Word, and Excel. So these can have embedded files, hidden scripts, and macros, which can contain certain malicious code or malicious executable. And then we have web scripts, malicious websites, malicious backend scripts, etc. So they also act as a dropper. Then we have all multimedia like images, videos, music, and it is possible that they are not actually doing something themselves. They are exploiting a vulnerability in the existing system. For example, suppose we have a video that is intentionally designed to, say, exploit a vulnerability in VLC. So attacks can be done like this also. And they are all integrated and combined nowadays. For example, let's follow this. We have, suppose, Excel document, and it has a macro. And otherwise, we have a PDF document and it has an embedded file. So these can contain some scripts, or these can contain some executables, which will be executed after we open the document. Otherwise, a website, a malicious website can have a executable that's malicious, a multimedia that's malicious. So that's how it spreads. So this we will again tap into when we will talk about feature extraction, and we will see how these different properties of malwares will help us in determining what to take from the malware so that we can differentiate it from a safe application and a malicious application. So any doubts till now? It's pretty simple, I guess. Okay. So we will go for basic detection methods. So we will follow this model of detection that we will see about signature-based detection and behavior-based detection. And in behavior-based, we have specification-based. We will talk about them in detail. And in every one of them, we have three categories: that's static, dynamic, and hybrid. So what is static and dynamic, and what is hybrid? So first of all, we will start with signature-based. So signature-based malware detection is actually we take certain chunks of properties from the malware and we make a signature out of it. Signature means just it can be a string, it can be a identification point, so that we can differentiate that malware from other processes. And behavior-based, we study and analyze the behavior of that malware, and based on its activities we will say if it's malicious or not, or what it is doing in the system. Is it just sitting there idly and doing nothing? Is it sitting there and sending information to other server? So we will see it. And then we have specification based. So we have certain specifications for the malware based on its behavior, and we will try to identify the malware based on that. So let's get deeper into static and dynamic and what we mean by them and what's hybrid then. So in analysis, we can either do it statically or dynamically. Static means we will not run the malware for now, and we will try to extract as much information as we can from the malware just by scanning the code, just by disassembling it, or extracting any information we can get from the raw file itself without running it. And in dynamic, we actually run the malware in controlled virtual environment where we can study its behavior. Okay, so suppose we have a malware M and we try to analyze it. So in static, we will just extract its properties and we will see what properties they can be. And in dynamic, we will run the malware M so that it will not actually cause any damage to our legitimate system, but we will run it in a virtual machine so that we have all control of that environment and we can study what it's doing in there. So let's start with static. So in static, we can check for structural properties of the file. For example, it can be entropy of the file. We can check if the file is compressed or not, it is highly encrypted or not, etc. Then we can do code analysis. If we are able to read the code from the malware file, we can check for certain things like function calls, code blocks, code patches. For example, if a malware or a family of malware uses certain function call every time they are executed, so we can identify it. Then if a file contains certain patches of code that are there in every malware of that family, we can identify it. And then file type. So we can check for the file header, the magic number value, which is in most of the files that tells that this file belongs to this application. And we can cross check it with the application extension provided. For example, let's say we have a PDF file which says document.pdf, but when we try to analyze it, it will say it's like MZ header file. So it is a PE file, portable executable, Linux, Windows executable. So these are the things which may trigger the suspicion. Then we can do string extraction. So we can check for phrases and words or other things which can be read by human, the ASCII characters, which are they are hard coded in the malware. So we can extract those from the malware, and these all are the properties which we extract without running the malware. We are just scraping as deep as we can. Then what else we can do is disassembly, and we don't do disassembly every time we try to detect it. It is mostly the part of analysis, and we try to analyze what's going on with the malware. So we can check for function calls from its opcode and the system calls it's trying to make, etc. The kernel calls, so we can have an idea that what it's going to do when it's going to be run. So let's move on to dynamic. So in dynamic, we can check for API call the malware is making. For example, the malware is trying to communicate with external server, so we will check for it. Then we can check for file integrity. For example, if malware is changing certain files in its closed environment, means the folder it is in or the privilege level it is executing on. Or we can check for critical system locations like uh, kernel files in Windows, the system32 folder in Windows, or the C drive. In Linux, we can check in the root directory, is it changing anything in the bin, etc. So we can keep an eye for that. Next, we can check for environment variables. So environment variables actually plays an important role in controlling other applications. Some applications depend on environment variables to choose their workflow. So a malware can change the environment variable and the applications will follow those settings. So we can check for global level, user level, and specific domain level environment variables when we are running a malware in virtual machine. So we will check if it's doing anything with those, if it's changing those variables to specific values. So this is also important. Then registry entries. In Windows specifically, registry is a powerful tool. Okay, so whenever a malware tries to infect a PC, even for going in persistence mode, it can alter registry. Registries can actually disable your keyboard, mouse, etc. just by changing the values. So that's one thing to keep an eye on. Then we have system calls. So specific system calls that malware is trying to make inside the virtual machine. Then process hooks. Is it trying to hook to some other process? Is it trying to migrate? Is it trying to, enter debugging functions in other running processes in the virtual machine? And then we have memory fingerprinting and memory injection. So memory fingerprinting works like we take a snapshot of the memory, image of the memory before running the malware, and we take one snapshot image of the memory after running the malware, and we will then compare them for the changes. So this will tell us if malware is trying to do something in the memory, or it is trying to make some memory executable, or actually we can check if it's packed in some case, or the actual malware is being injected in the memory and then run from there. So these are pretty important things when we analyze a malware, and we try to make notes of the things we can use to detect the malware when we are in detection phase. Here, memory fingerprinting and memory injection check are closely related, and the two system calls are actually, the concept is same. We want to check the system calls in static and dynamic, but the process is different. In dynamic, the malware actually calls for the system calls, and we can just check if it's making it or not. In static, we don't know if it's calling or not. So we have to uh, assume the system calls from the given opcode. So we will match the opcodes to the system calls we know, and then we will say that yes, it may call that system function, kernel function, etc. So any doubts till now? Like, is it making sense?
Yes.
All right. So now let's see some disadvantages and advantages of signature-based and behavior-based checking. So right now we talk about everything like how behavior-based and signature-based works, and what is static and dynamic properties. So they have certain advantages and certain disadvantages, and because of those disadvantages, we are going to use ML. So it's important to first check out those disadvantages. So advantages of signature based are they can detect malwares easily. Like known malwares can be detected very easily, and it is less uh, resource eater than this, the behavior base. It will just check for static features and specific parts of the malware. And one problem and one critical problem is that unknown malwares cannot be detected because we have signature of a specific kind of known malware. And a small file mutation, small code mutation can change the whole signature and pattern of the malware. So our trick to identify malware from signature will not work then. In heuristics or behavior based, the advantage is we can detect known and unknown malware as well, because we can just say that this application is not behaving correctly. It is behaving like an malware. So we may quarantine it for some time for further processes. And the major disadvantage is we need to update regarding new malware properties over and over again. And these updates grow larger and larger in size over time. Then we need more resources for this. Like we need to study the properties and behavior of malware. And every time we are going to detect it, we need heavy resources of computer so that we can analyze the behavior of the working process. And the level of false positive is very high. So a great example of false positive is when we are trying to, there are many trainers for the games available when we play, if you play games or you do some memory forensic stuff, some of the softwares are declared malwares. Why? Because they do memory injection. They alter the memory state, and they're doing it for reasonable cause, because game trainers and game cheats will try to inject a specific value in your health bar or your armor bar, etc. They are not damaging your system files, but it is a property of malware, so they might get stuck in that filter. And then we have some memory forensic tools. They can also be detected as malware because they also alter the state of memory in the computer. So false positive is pretty high. So that was all about how we use uh, malware detection and what things we use in it. So the static properties, the dynamic properties, and when we combine all those properties, we come with the hybrid properties, like we use some of the static, some of the dynamic, etc. So let's discuss about basic idea of machine learning in detection. So the basic idea of machine learning is, first of all, we will talk about what machine learning actually is, and a difference between machine learning and deep learning, and where it stands in overall artificial intelligence scenario. And then we will talk about what we need to do to identify malware from machine learning. So let's talk about machine learning and artificial intelligence. So machine learning is a subset of artificial intelligence, which uses statistical methods to enable machine to think like a human in the way like we improve with our experience. We do something, we see it's not wrong, it's not right, and we should not do it, so we will learn from it, and next time we will not do it. Okay, so this is how we learn. So we try to do that. In deep learning, it is more advanced part of machine learning, where we use multi-layer ML models and machine learning techniques, and we try to create a neural network similar to our brain and how it works by creating different layers of patterns and uh, you know different layers of ML. So this is what we will talk about, and in this talk we are focusing on machine learning part. We will not talk about overall AI, and we will not talk about specific deep learning. So let's see. A computer program learn from experience E with respect to some task T. Like suppose we give it to identify malware, and we have its actual answers, and we will train the model so that it will try to establish a relation with the answers and the questions. All right, so suppose we say 2 plus 2, and we have the answer 4. So we will tell the machine the answer and the question, and we will tell multiple answers and questions so that machine can actually derive some relations between them. And after a certain amount of training, we will try to check if it's learning something or not, or if it's able to deduce an answer if we are just giving it the question based on previous experience. Next, in deep learning, we try to let machine create its own definition in different layers, and it will establish multiple relations with the question and answer set. And it is like more less controlled, and in its machine learning we control it, every aspect, every parameter of it. In deep learning we will just send it to the machine, it will extract its own feature, and it will try to establish a relation between them. And we use deep learning for complex tasks where much more data is used to identify something. And in machine learning we can do for some statistical mathematical problems, like which can be done by statistics. So, um, okay, so in this talk, we will talk about machine learning specifically and how we can use that to identify and detect malware. So let's see, we have uh, two scenarios with us. First of all, we have to build a surveillance system which will scan the faces of people and raise an alarm if they are not recognized from the database. And next, we have a bank's transaction detail and credit transfer history, and we have to detect the fraud transaction. So what do you think we will use in scenario one and scenario two? Uh, Machine learning or deep learning?
I think my guess would be like machine learning.
Scenario one,
Yeah.
okay. And for two?
Deep learning would make more sense for.
All right, so well, let's see what we have in the scenarios. So in first scenario, we have to recognize the faces of people, and they are like way complex than they seem to be. Like we have uh, features of faces, the uh, specific points we have to trace to identify one person from other. And this requires much more computational power, and it has a large number of feature set to be identified. And in the second scenario, we have specific information like bank's transaction details will contain time of transaction, amount of transaction, duration of transaction, etc. So we have certain specific and known things to calculate. So for the first one, we will use deep learning because it's more complex and we have less control over it because everyone's face is different and we don't know which property will set where. In second scenario, we know about most of the properties and we control those properties so that our machine can learn. So in second scenario, we will use machine learning. Okay, this makes sense.
Yeah.
All right. So then let's talk about classification. So as we see here, uh, we can use machine learning for different purposes. For example, we can predict things. You might have heard of predicting stock market prices from machine learning and AI. And we can classify cat and dog on machine learning and AI. These are pretty famous examples and initial implementations of machine learning. So what they are doing in prediction, they are predicting something. They don't know the value right now, and they try to project uh, something in future. In classification, we have two classes, and then we try to identify to which class the new object belongs to. And then we do clustering. In clustering, we don't know how many classes are there. So we will just cluster them according to their certain properties. And then we try to see in which class does our new object falls. For example, we have images of dogs and cats. So we train our model on those images. So properties of dogs will be clustered in a graph somewhere, and properties of cats will be clustered in a graph somewhere. And when we have a new image, say a dog, and machine does not know that, so we will feed it to the neural network and it will check the properties and it will try to plot those properties in a graph. If they fall near to the dog section or the dog class, we will say that it is a dog. If it falls near the cat section, we will say it is a cat. All right, so this is how it works. Like we try to identify to which set of categories does a new observation belong on basis of our known information or known instances. All right, so this is the basic definition of classification. So we have certain algorithms in machine learning for classification. We will not talk about all of them in detail because they are just another chapter of machine learning. And they can go in so much detail. But we will talk about, or we will just try to understand some basic machine learning algorithms. So first we have SVM, support vector machines. So what we do is we create two vectors uh, of two different classes, and then we try to take the mean of those, and we have margins, and um, then we try to plot the new uh, vector or the new observation we have in these. So if it's falling the right side of our separating hyperplane, it is in positive class, and if it's falling to the uh, left side, it's the negative class. So actually these have furthermore explanations and much deeper mathematical equations. So we will not talk about that right now. It is not in the scope. So, but it's pretty interesting thing how they work, how they use mathematical equations to create and separate two different classes and properties plotted on a graph. Then we have KNN, K nearest neighbor, where K is a variable. So suppose we have plotted these two categories on a graph, and our new category is this yellow point. So it will scan for the nearest 5 neighbors. In this case, we can change the value of K. So in this case, this is 5 nearest neighbor. So it will check who is close to me, right? We will check, okay, the first one is blue, second one is blue, third one is green, fourth and fifth is green. Now we have 2 blues and 3 greens. So who does I belong to? So as we have majority of green here, so the new point will be in category A. All right. So this is the most basic explanation of KNN. So there are different methods to how to cluster them according to their properties. Sometimes we cannot see the clustering in one plane, so we have to project those points on other plane so that we can somehow separate them on the graph. So these are just the basic, and uh, you can read about it more, and I have resources, so I will upload them on Git so that if anyone is interested, they can read more about it. Then let's talk about what steps we need to follow to detect malware from machine learning. So first of all, we collect samples. As we saw, we need experience to learn from machine learning. So we need to collect certain malwares and certain good applications from, there are many sources, so we can download any data set from internet. And in our research, we have used Androzu for Android and Ember dataset for Windows. So that's the sources of where we can download malicious and safe applications. Next, we will do feature engineering. We will extract certain features from the malware and benign applications, and then we will try to train our model on that. And features are certain properties that we look for in a malware and benign application. And then the machine learning models will create certain relationships from them, and it will deduce that whether it is a malware or not. Then we will train and test. So this is actually important, how we train and test, we will see into it. And then we have deployment. We will deploy the model and it is ready to detect. So let's see feature extraction of malware samples. So question is what we should look for in a malware. We have many things. We talked about all the static properties. We talk about all the dynamic properties, what we should look for. So this question actually depends on what kind of malware we are talking about. Are we talking about mobile platform? And in mobile platform, are we talking about Android? Then we will check for permissions, API calls, user level interaction, etc. So we will scan those. If we are talking about executables, like suppose we are talking about Windows machine, so we will check for DLL, dynamic link libraries and imports. We will check for opcodes, etc. So we will define our features depending on what we are targeting. So this actually depends on what we want to extract from the malware, and the type of malware actually. Every feature engineering depends on the type of question we have, and then we will try to collect all the answers. Next, here's a short dissection of a Windows executable so that we can see what we can extract from it. So a simple exe file contains two parts, and those are divided into many subparts. So we have header. This contains technical details about the executable. For example, eh, it's whether it is executable or not. First of all, that how many sections does it have? Like we have text section, BSS section, data section in any executable. So it will check for if it will have information for those. Then in later sections, we have actual code of our application. So whenever we type a C code or a C++ code or any language's code, we when we compile it, we actually just don't have the code of that in the file. Our compiler adds multiple information layered over each other so that when we run it, our system knows how to handle our code and what the resources are needed for successful execution of those codes. So these are information present there, and we just need to extract them. And there are multiple tools from which we can extract it. We can also extract it manually. We will just see in a demo how we can extract it manually. It's pretty cool. And we can use those features, like we can check for code segments, we can check for specific imports we were talking about. And these are all in binary format. So this is how it looks like. This is a hexadecimal representation of one of the executable files, and sections are not actually divided by these lines. They are just regular continuous values, and we need to identify them. And we can do it with the help of software or analyzer, or we can do it manually. Just we need to have knowledge about where we should look for. So for example, let's see what we can extract from this. So we have here 4D5A. So it is actually a magic number which tells us that this is a MZ header, means this is a executable, Windows executable file. And then we have PE header, which will tell that is a portable executable exe file. So, and so on. Like these values say something about the application, and we can extract these values for identification purpose. So this is how it looks. Just this is was to give an idea of how actually the data in the malware or any application looks that we are targeting. Then, so now we know what to extract. We know we have to extract these data. We know we have to extract text. We know we have to extract import tables, etc. And we know we can do that with the help of some software available. Like Rare is a software for reverse engineering, and we can also use it to extract certain information. Like we can use Rabin 2 is a tool. We will just see how it works. So we can extract information from it like that. So now we know how to extract it, but we need to have a well-defined structure to store it, because we know how it works. We know how we are going to identify, but we need to make our computer understand that why we are extracting those and what they mean actually. So there are multiple ways to store the data, and we will see one of the ways that I used in my research. So because I am familiar with it, so I will be able to explain it better. And there are multiple ways to store information, and it all actually depends on how efficiently you store them and how you are using those information for training your model. So for example, we have the binary array approach. Many people call it binary array approach. Many other may call something else, but this is pretty simple and widely used approach. So what we do is we collect all the properties from every application, including malware and benign, that is our malicious and safe applications, and we create a list of all those, because all the bad behaviors and the good behaviors, we will make a list of all those. Then we will take one sample at a time, and then we will check if its properties are present in the global list of features. If it's present, we will toggle the value to 1, otherwise we will toggle the value to 0. So this will tell our computer or our program that the specific malware, say M, has these properties like 4th, 5th, and 6th properties, and the benign application, say B, has 1 and 2 property. So it will create a relation between those, and it will detect the malware based on those relations. So, and we can save this in simple comma separated value CSV file, which can be opened in Excel. So we will just see how it actually works. So let's see a demo of feature extraction and how it actually works. So I have this data set. It has all the features, and everyone can see my screen, right?
Yeah.
Yes.
All right, so we have these features data set. I will just open a terminal here and I will try to show you how this is stored. Let's make it bigger. All right. So it's pretty big actually. So I think, can you see these ones here? These ones?
Yeah.
And all the zeros. So I have one more clear picture of that I took, and I just colored all the ones here. So you can see all the ones in here and all the zeros. So suppose this is our application, the mediaplayer.apk. This is an Android application, and we did this on permissions. So we had a set of permission, and if this application has those permission, we will click that to 1, or otherwise it is 0. So you can already see that it creates a certain pattern in our canvas of zeros, right? So we can see already that there are some patterns in every application. And when we were looking into it like this, so actually I discovered something that these patterns actually match up with the same kind of malware families, and that was pretty interesting. So this is what we feed in our neural network or our machine learning model. So this is how it is stored in a simple Excel sheet, or you can say this is one of the methods to store it. You can also store it in JSON format or etc. So yeah, so this is the same screenshot. How we store it, and now we know how to store the malware, like how it is stored. Is it clear? Like, does it make sense how we store the information?
Yes.
All right. So uh, now we will see how we train model. So usually when you will see about machine learning, we will see that we divide the data set, the information we stored, into different parts, like training part, testing part, validation parts, etc. So in training data, we use it to actually learn the patterns from the data, and we create a model from it. Then we have validation data. So we use this to tune our model properties, because as we said, it is actually a combination of mathematical functions. Now for each mathematical function, we have certain values in which the function performs excellent, and if we jeopardize that value, the function will collapse or it will not perform as expected. So it is important to tune the function for maximum performance according to the data it is given. Then we have test data, and this will actually uh, create a performance model of the training set. So we will be actually able to see if the training data is working or not. So this is one more good example of training and test data set. So we have original set here. We have divided it into two parts, training and testing. And then we have divided training part in two subparts, that is training and validation. So we use validation set for evaluation and tuning the model, and we use test set for checking whether it is right or wrong. Suppose in test set, we know the answers and we know the questions, and we will inject those questions in our machine learning model, and we will see what answer is it giving to us. And then we will compare those answers and we will see, yes, okay, this much answers are correct, this much answers are wrong, just like ranking in examination. And then we will give it a score and we will see how good is it performing in classification or any um, thing we want it to do. So we have certain uh, uh, models or matrices to check for um, performance. We have confusion matrix, F1 score, area under curve, that's AUC, and root mean squared error. So again, they are just a whole different chapter, how they work. Just we can see one example of confusion matrix, and so that we can know how it actually works. So suppose we have 165 uh, information sets, we have 165 elements, and then we try to predict them. So our predicted value is no and yes. So it is like yes or no. If we give our machine learning model something, it will tell us yes or no. So first of all, it predicted 55 of them as no, all right? And it predicted 110 of them as yes. And now we will check, actually, are they no, or as we know the answer, so we can just check it out. So they predicted no, and the actual value is also no. So that's 50 of them. And 5 of them were predicted no, but the actual value was yes. So this is false negative, because it's saying it's negative, but it's false. So we call it false negative. And above it, the 50 value, it's true negative, because it's saying it's false, and that's true, it's false, so it's true negative. And so on, like we have here yes, so its predicted value is yes, and actually we have no as the answer, and 100 of them are predicted good. So in here, if we see this diagonal, the true negative and true positive, we try to increase those numbers as much as we can. And then we have these diagonal, the 5 and 10 one. So 15 of them were reorganized incorrectly and was wrong answers, because they were predicted something else than what they are actually. And 150 of them are good answers, and we want to increase this number. So this is how we can get an idea of how our model is performing on the task we have given. And on basis of this, we can try to enhance the model by changing certain values and etc. So this is how it works. Now, does this make sense? Is it clear? Okay.
What is the confusion matrix for?
This is to check the evaluation of our, the model. Suppose as
So the
we
testing phase.
Yeah, the testing phase. We have the testing set here. So in this testing set, we test the model for accuracy, right? So we have trained the model, it is giving us answers, but we want to check whether the answers are correct or not. So one way of doing it, to ask the questions whose answer we already know. So we can just compare the two answers if they are matching or not. And just like we give exam, the examiner knows the answer, then a professor knows the answer, and we just give them the answer and they will check whether it is correct or not. So, and the result is presented in form of this matrix, so that we can, check whether our model is working good or not.
Yep, makes sense.
All right. Okay, so let's see a small demo on how model testing works. And I have just a small video I have recorded for that. So we will just see it. Okay, so we have these files B, M2, and M.exe, and M are malwares and B are safe files. So I have that Python script we created in our research. So I will just run it. And here you can see in the Python script, I have mentioned b.exe. So it will scan b.exe, whether it is malware or not. And then let's run it. And you can see that here it says that it is a safe application. Okay, so it says it is a safe application here with accuracy of 99.5% that it is safe. And we can check for the another application just by changing the name. So we will just change the name in our code to m.exe instead of b.exe. We have commented out the b section and we have selected m.exe. Now it will scan that file and extract its properties and compare it with the already trained model and try to make a relation. So now we can see that it is classified as malware, and which is the case. The M1s are actually malwares and B1s are actually benign softwares. So does this make sense? Like, was it informative that how it actually works, or you are able to relate it, right?
Yeah.
Okay, so let's start with the continue with the presentation. So now we know that we can do this. We know we can, train model and we can try to detect the malware from it. So next up is just a proof of concept. We will not go much deeper into this because this is a whole new domain, and we will try to evade feature detection like these models. Like we know how we can detect the malware from machine learning. Now my current research is on how we can evade those detection. And after this, we will see why we can use multiple ML models to, enhance our detections. So in this, we will try to evade the malware from the ML detection. So for evasion, what we can do is we can hijack the data set, right? We know already that we need certain information already so that we can train the data set or train the model. So what if we can hijack and alter something in the data set? So in that case, we will have disformed data to begin with, and the model will not be able to identify correctly. But this scenario is very, very rare, and we do not consider it because every training and testing of model is done on isolated machines in every major companies. They don't share their testing and training models with anyone, and they are heavily protected. So because they are key features for the whole ML architecture, if the data set or the information source is wrong or corrupted, the whole system will fall apart. Next, what we can do is we can target specific features. If we know that the ML model search for certain behavior to say that it is a malware, so we will just not do that. If it search for altering files, we will not alter files. We will do something else which is similar to altering files, like writing the file and saving it again instead of just directly altering the file. Or we can just do something else which will achieve our goal but not trigger that action. Or what we can do is called adversarial machine learning. So this is an interesting field also. So we can use machine learning to defeat machine learning. Like we can learn how to detect malware, the machine learning models can also learn how to evade malwares just by having experience. Okay, so for example, this is a popular example of how adversarial network works. So in researchers, many researchers, they have done on image processing. The model was first detecting these image as panda, and that's actually right. It's 57.7% confident that it is a panda. But after adding some specially crafted noise or randomness in the image, we can see that model is now 99% sure that it is a raccoon. All right, so this is a major field in ML, how we can fool the machine learning model just by adding some noise in the actual image. And this is what we are trying to do with malwares. So instead of using machines, we are using malwares. So our model just said that panda is equal to raccoon. That means if we are using that to stop someone or stop some panda from entering our facility, and we are allowing raccoons to enter our facility, we will just allow a panda to enter our facility because our model says so. All right, so this can be a serious property or attack, or it can be a minor attack depending on the implementation of the machine learning models. So again, we have one video, a small recording to see how that works, like AI evasion, and it's pretty interesting. So we will see how it works, and it's pretty cool how that works. And all these resources I've also uploaded on Git, so I will share that with you. So this is our evasion setup. We have a malware X, which is stored as data and disabled so that it cannot run on system. It is active malware. And what we will do is we will try to evade it. So as we saw earlier, it is the same malware, 94% malware and 6% safe classification one. And we will mutate its properties like genes in human body. And then we will try to evade the scanning phase. And let's see. So it will do 5 rounds of mutations, and then it can evade the malware detection. So now at the end, we can see it is declared safe. And our model is actually 51% sure that it is safe because we mutated certain values and certain properties of malware. And now it can bypass the whole malware detection architecture. So this is ongoing research what we are doing here. And this was just proof of concept to show that it can be achieved. Here's another example. We have achieved 73% safe confidence in the malware, which was earlier 94% confident that it is a malware. So this is pretty dangerous threat that if we are able to evade certain malwares from machine learning models that are the latest in the field, then we can do much harm. But this is already in development phase, and I have not seen any example of it in actual life because both the technologies are in research phase, and some companies like Kaspersky and other are using it to detect, but they are using it with other pre-existing methods also. Nothing is solely ML based. So here it comes the importance of using multiple ML models. Suppose we have one guard and our Mallory is able to fool that guard. But if we have multiple guards, so maybe it will be trapped by one of the guards if it is able to fool 4 of them. So this is the main concept of using multiple models. So this was the research we did on Android applications where we used Android malwares and trained our models, and we presented that in big data analytic for cybercrime and investigation and prevention IEEE conference in Las Vegas. So what it was all about was an implementation to access several machine learning models, just like the one we saw, and that was one of it. And we have several like it. So we use that and we try to get certain threat intelligence, and we try to detect malware based on that. So this is the main architecture of it. We will not go in detail. I will share the research paper with you guys in Git so that you can read it all. But for now, let's see how it works. So we have multiple ML models here, and we prepare them with multiple benign and malware dataset. And then we train those models and we store it in database. And whenever user try to interact with us, we can scan the given application with multiple models, and we can form a good report out of it. And our user can access the framework via different interfaces, and it can be targeted to different set of users like general user, IT professional, or the cybersecurity researcher. So so this is how it looks. So this was the main screen of PACE. So here we can upload our file and it will analyze it and it will show us that the Android file contains 20 permissions. It is detected by as malware by 8 of the model. That is all we got. So 0 safe hits and 8 malware hits. And it will also give us a good entropy chart of detection. So it is a comprehensive uh, intelligence about the specific kind of malware. And over time, when we try to use multiple models, we can understand the specific kind of malware and
Saket, you there?
there are 9 models and their results. So see here, the 8th model does not show any result. So it is not able to detect the malware. And others are able to detect the malware. So just in case we only employed one of them, the malware would have evaded this. But as we have multiple models, it is being caught at some stage, maybe at earliest stage or later stage. And these are the base operations it works on, like we talked about: support vector machine, random forest, KNN, just we talk about, and other things. So these are done by different researchers and we have credited them all for the research. So the other models are not our work. We have just integrated those models from their researches so that we can show that how we can use multiple models to uh, detect malware and create a good analysis report. And here you can see uh, it can generate multiple reports in form of charts, graphs, so that we can understand it more accurately, and it will enhance the whole experience. And it is like information at one place. So if we use multiple ML models, we can just have a enhanced view of the malware itself. And here we have all the permissions of the application we submitted, and we can check if it belongs to stock or not. Stock means what Google provides you as default. So writing to external storage is not a general uh, permission. Accessing camera, accessing phone state, deleting packages, and accessing network state, installing shortcuts, these all show that uh, th this is something wrong going on with the service, because uh, why would an application need all of these at once? And maybe it needs it, but there's more chance that it's doing something else. So this is how it works, the whole architecture. We have all the properties of the malware and it is all compiled in one report. So that was it, how we can use uh, the things. Now, the closing thoughts are that it is a very crucial phase, the malware detection and elimination in defending a critical digital infrastructure. Let it be a company, let it be an institution. A malware attack can cause lots of damage financially and um, at the tech background also. Then we have advantage of AI and ML, but we need in infosec and cybersec, and the field is adapting significantly with that AI and ML, and it's pretty good. But we need to know that these technologies are with defenders as well as adversaries also. So if we are trying to use ML to defend our system from malware, adversaries or malicious people are also using the same technology to invade in our computers. So this is again a race. And there's a lot more to explain. These are just ongoing researches and implementation is just starting to come up. So this is a good research area also. Then these are some due credits and mentions. They helped me with the above discussed research paper. And so, okay, thank you guys, and we can have question answer. If you have any questions after this talk, or you want to talk about the topic anytime, you can just feel free to contact me on any of the above. And I will upload this presentation at this GitHub repository, and I will share this with Ray or anyone like you want, I will just share it to one of the person, and you can see all the practicals, demos, and you can do it yourself. It contains many things like codes and other things. So yeah. So if we have time, we can just, you know, have questions or, all right. Okay.
Yes, that was a great presentation. I didn't have there was a lot of info to
All right.
kind of take in and parse through. But I don't have any questions right now. Does anybody else have any questions? Okay, well, thanks for coming out, Saket. We look forward to working with you in the future.
All right.
I'll
Thank
make
you
sure
guys
that the
for
club.
having
I'll make
me.
sure that the club has your contact info if anybody wants to get in touch with you.
All right, thank you. I will share the GitHub repository soon with you, or the Ray. And all right, thank you guys for having me. Thank you very much.
Have a good one.
Yep.